So, Sasha, thank you for the great intro. As a few people in the room, I've been part of this circus since the beginning and enjoyed many wonderful events, lectures, friendship, professional interactions. So thank you for inviting me again, for keeping me on my toes for so many years. I think it's a special year because not only should I thank Professor Warnick for inviting me, but also congratulate him on winning the Skolnick Award from the American Chemical Society this year, which a few people in this room are going to be attending and speaking at this event. And in addition to his multiple scientific contributions, he was also acknowledged for these workshops, for training generations of chemoinformaticians and allowing us to get together and exchange scientific ideas. So congratulations and thank you for a lot of service to the community that you've done over the years. So I'm really honored to speak here. Thank you also for giving me an impossible task. Because when Sasha approached me, he said, just speak about everything, the entire field, in less than 1 hour. He restricted me, unfortunately. And that is to explain a subtitle of my talk, which is that you're going to hear comments from a sarcastic but optimistic chemoinformatician, which is how I describe myself. And so hopefully will be a combination of notes about the past and present and future of the field. And I will start with a philosophical comment to explain the title of the lecture, because I think it's somewhat self-contradictory, reminiscing about the future. But apparently there is a field. There's the entire field called reminiscence, and these comments are coming from a paper published in the International Journal of Reminiscence and Life Review. You can't imagine how many journals exist these days. You could find, whenever you have some idea, you could always find something published. But it's actually quite interesting. Reminiscence, by definition, involves recalling episodic memories from one's personal past, which is how we started. This is memories about these workshops. This process often triggers thoughts of the future. So think about this. I think it's actually accurate. And conversely, imagining our future can frequently stimulate reminiscence. Most interesting, what I found is that not only past and future share certain properties in common that are distinct from the present, which is where we are right now. And the present is the least attractive, the least interesting. Because both past and future are infinite. In contrast, the present is coming into being and slipping away, lasting perhaps less than an hour of this lecture. So that's my intro. I think it's pretty profound, and fortunately, I found something. So here's the outline. As advertised, I will talk about the past, the basics, the reminiscence, but I'll try to position reminiscence in the context of present and future research in chemoinformatics. And I also found these words from Chris Ray's famous song, The Blue Cafe, which I think applies to this field. Where have you been? Where are you going to? I want to know what's new. I want to go with you. And I think that should define the essence of studying chemoinformatics for all of us. And I will make a point that the good and old days chemoinformatics concepts are still valid. So hopefully you will agree. I'll talk about recent developments as well as warnings, and that will be a somewhat sarcastic part of the lecture, discussing sense and sensibility of chemoinformatics, that now we use the word deep always as we discuss this concept, on occasion throwing in terms such as AI and other forms of learning. And then the future, the impactful trends. And I think the most impactful trend that is reflected in the field is that it has become a big data science discipline with everything that big data science brings into the challenges that are facing us. So I'll start by the foundations of the field. In 2009, the Journal of Chemoinformatics was formed. And the very first issue, there were grand challenges that were defined. And as I'm not going to read this to you, I'll let you read, but perhaps you could see that the same grand challenges can be formulated today almost entirely the same way, except perhaps that we're dealing with the different types of data, different volumes of data, and different technical challenges. But philosophically, the grand challenges, such as drug discovery, green chemistry, understanding life as chemists, and enabling networks of information and connected knowledge to be explored, these are still big challenges in front of the field. So it's good because it only illustrates how fundamental this discipline that at some point was coined and called chemoinformatics is. So I'll go through a very few concepts that I consider key paradigms of the field. And overall, and that has become and is becoming, I'll reflect on this, more and more important that the computations are done in the name of experiments, fueled by experiments, processed computationally, but it's always important to remember that in the end, we want to use chemoinformatics methods and tools in order to affect in the most plausible way the experiments and inform and increase the experimental hit rate. It's also important, and still important today, to recognize, and it's one of the most wonderful papers in the history of the field, how not to do research. And I, again, will talk about how not to do research today and how some of these concepts, especially those that I highlight, are still found in the field and many publications in the field. But for those who are relatively new to the field, knowing how not to do research continues to be very important. And learning about 21, in fact, it should be 22, key rules of how not to do research in chemoinformatics is very important. Error detection has been, continues to be one of the key elements of chemoinformatics research. And I would like to emphasize and re-emphasize how important it is to pay attention to the quality data, especially as we process large, massive data today. And here are just a few examples of the types of errors that could be and continuously found in databases, especially duplicates, which is a special case where data should be properly treated for chemical duplicates and chemical duplicates that have differential measurements associated with this. And the existence of errors in databases affects both simple and very complex models and continues to affect it. So protocols have been developed and continuously should be applied in order to curate both chemical data, and we and others have developed special protocols going methodically and systematically through chemical data and curating accurate and presenting chemical structures accurately, as well as, and that is even more important, dealing with biological uncertainty. And there is an aspect of data curation that I always highlight, and that is that one could talk about canonical chemical structures and curate chemical structures accurately, with some caveats where it's impossible, such as multiple chiral centers that have not been resolved, or tautomers that have not been resolved. But for the most part, canonical chemical rules can be applied to curate chemical structures accurately. But when it comes to biological data, there are no canonical measurements. Biological data is inherently inaccurate, perhaps irreproducible, so a lot of attention needs to be paid to processing data and eliminating duplicates and looking at whether or not duplicative chemical structures after curation have identical or dissimilar properties associated with them. So this has been and continues to be fundamental aspects of chemoinformatics research. And then how we model the data, how we process the data, and how important continuously is to think about prediction for external data sets rather than overemphasizing the quality of models developed for the training set, which we could continuously, especially with big data, and I'll allude to this, also overtrain models, or the more powerful algorithms we use, the more is the chance that the models are going to go overtrained. So it's important to figure out how to convince yourself and the world that the models that we've built with past data can extrapolate to new data, and what comes with this extrapolation, what kind of precautions we need to take to assure accurate extrapolation of models developed on the training set. So to deal with these issues historically, another key paradigm, applicability domain, which continues to be a very important part of modern research, how to define the applicability domain. It now has slightly different name. I'll talk about it, but the objective is to recognize that no matter how large our training set is, it has limited size, and extrapolation can be reliable only in certain directions in the chemistry space and within proximity of the training set that needs to be defined. The chemical space needs to be defined, and the proximity to the training set needs to be defined quantitatively. And the associated predictions can be reliable or less reliable depending on how we define the applicability domain. And then some concepts that have been developed, which I also find fundamental, such as whether a data set can be modelable. And it's a funny word, modelability of the data. But empirically, I think every cheminformatician at some point had found out that the data, for some reason, the modeling attempt perhaps looked great for the training set, perhaps did not even look great for the training set, but the extrapolation has been repeatedly unreliable. And so we've defined this concept of modelability and index that we've called MODI, which effectively is a one nearest neighbor model. And if a data set has a large number of nearest neighbors with different designation of the target property, that particular index that calculates the fraction of this formal property cliffs or activity cliffs turned out to be a very strong and simple indicator of our ability to develop or not develop a model that can extrapolate well. And here is also an observation from the same paper that defined MODI, and that is that what we've demonstrated is that if we take a large number of data sets and calculate this simple MODI index, one nearest neighbor model, what we find is no matter how complex, strong, deep algorithms we try to use to establish a model of high accuracy, if the MODI index is below 0.6, no matter how much you try, you typically are unable to develop a model of sufficient accuracy. And that's just the property of the data. It's a point I'll come back to. And I've chosen some points that I will come back to sort of in a new way, reflecting the recent developments in the field. And then a couple of more points that I want to make from the past, which again, I find important to share and emphasize as part of classical, historical, fundamental cheminformatics research. One is how we convince ourselves and the world that the model is accurate. And here's one of the standard errors that have been articulated on how not to do. QSAR by John Dearden, and that is we need to be mindful about the distribution of the data and what comes with it. Many data sets, I'll come back to this point too, are imbalanced. And here is a simple example that if a data set has 4:1 ratio, 80 molecules of one class and 20 molecules of another class, if we just calculate total accuracy, which is the most intuitive and most immediate attempt that one makes, then the total accuracy is going to be 80% without even building a model. If you say that everything is class 1, all 100 molecules and 80 of them are class 1, you're 80% accurate. And so that certainly does not make sense, and therefore more specific metrics need to be considered when, and for the most part, data sets are imbalanced. So in this case, a balanced accuracy calculation or correct classification rate, which is essentially the same as balanced accuracy, when applied to the same data set, immediately shows that the model on average is 50% accurate, right? 100% for one class, 0% for another class. And so we've always advocated for data set balancing before you run calculations. And the reason for this was that when the data set is imbalanced and you have small number of objects in a smaller class, then there is a rather small number of chemicals similar enough to the molecules in the training set of class 1 that make it relatively difficult to build a classification model. And if you increase the size of, if you don't downsample, if you don't balance the data, you make the task of developing a model easier and easier, the more imbalance is in the data set. That's what we always advocate. The data set needs to be balanced to make the task of classification model development more difficult, because you are discriminating a small number of instances from another small number of similar instances. And maybe we're recommending that the similarity-based sampling and downsampling of the second class, bigger class, needs to be accomplished. I will come back to this point because that's a great example of change in paradigm reflecting the new trends in the field and an understanding the data associated with the field. The final point I want to make is, and it's a very popular topic, so-called explainable AI in today's world, is how models, or can models be interpreted? And a typical statement of interpretation simply means that we are identifying or emphasizing specific chemical functional groups, a small number of descriptors that have the highest loading in the chemical sense, and essentially reduce the model and reduce the interpretation of the model to a few statements about chemical functional groups that are important, or a subset of descriptors that is important. And what I show here to illustrate this point is a distribution of descriptor values for a particular data set. And then we calculate how descriptor values change when you go from one molecule to another. And what I want to emphasize here is that a minor perturbation of the initial molecule affects nearly every chemical descriptor that we calculate directly from the chemical structure. And as we run this highly similar molecules, every single descriptor is affected. So there is no objectively specific or any reason to say that one descriptor really explains the entire behavior of the entire molecule. And so it's very critical as we struggle, because chemists always want explanation, as we struggle to explain statistical models. It's important to remember that chemical features never act in isolation from each other. And when you modify a molecule, multiple features are getting affected. And therefore, explanation of multivariate models by one or a few descriptors is typically nonsensical. There are ways of taking into account, and I love this out, but in general, we published about how you combine model interpretation if you absolutely forced by whatever reason to identify a few chemical features that are chemically modifiable, for instance. You could use global QSAR models in order to evaluate predicted consequences of a small chemical modification, which is always local. So there are some ways of dealing with this, but this is a very general statement, which explains the impossibility of simple interpretation of chemical models. And that I wanted to start with a few notes, just kind of to position ourselves with respect to the history of the field of chemoinformatics and some key concepts that people have formulated and elaborated upon in the last 20 or so years since the name of the field was coined. And now let's talk about recent and current developments and some warnings associated with these developments. And that's what I will allow myself to be somewhat sarcastic at least. So sense and sensibility of deep chemoinformatics. And I want to highlight and emphasize how important it is to read beyond current literature and relate what we do today to what has been done by wonderful and great scientists of the past. And I personally want to acknowledge three scientists from all of our recent past. One is Archimedes, who worked a few years ago, as all of you know, who presented an incredible case of ingenuity in solving a difficult problem using relatively simple means, right? And determining the density of the crown. And then getting excited. Somehow, when I was looking for the history of Archimedes, the most exciting story associated with him in majority of sources that I saw was that he was running naked on the streets, not the scientific content of the discovery. And then, of course, Isaac Newton, one of the most famous statements, which is very accurate, and I always find it as inspirational. If I've seen further, it's by standing on the shoulders of the giants. So again, there is a tendency not to read the past literature, and here is a statement from one of the greatest minds in the humankind who had explained how studies and education should run. And finally, Albert Einstein, who came up with what I will refer in the end of my lecture to as a universal formula of research and discovery. Because I realized that this particular formula has much greater value than what Einstein initially contemplated. So, what's new? What new happened in the before sort of in the recent history of chemoinformatics? That's the next section of this lecture. And what I've used in order to highlight what is considered current challenges in the field are blogs that one of our colleagues, Pat Walters, of Relay Therapeutics, has been formulating. And so Pat publishes blogs, very profound, highlighted and educational. So those of you who have not read his blogs, he publishes maybe 3 to 5 blogs a year, where he addresses current challenges in front of chemoinformaticians. And in 2023, 2024, a few blogs that I summarized here sounded awfully familiar. If you recall how I cited the Journal of Chemoinformatics. So what do we need to do today that we did not know or that we did not do 20 years ago? We need better benchmarks for machine learning. We need valid structures. This is the quote: consistent chemical representation and account of stereochemistry. Consistent measurements, realistic dynamic range of the data, fundamental for chemoinformatics, and cutoffs that we use when we transform data into a format that enables classification model. Data curation explicitly. And here is a funny story within a recent blog. There is a blood-brain barrier data set. There is a classical benchmark data set called MoleculeNet that people have used in hundreds of publications. And that's Pat's observation. The data set contains 59 duplicative structures. 10 of those duplicative structures have different labels. And yet hundreds of papers are published, including today with the newest chemoinformatics, machine learning, AI, deep learning, deepest learning, super deep learning, incredibly deep learning, and all of that are published, are claiming superiority over previous models by about 0.0005 AUC, which is the most common type of publications these days when the field is flooded by people trained in computer science, but not necessarily in chemistry. And so they're trained to compete on benchmarking and validation. And unfortunately, they're not trained to think about the type of data that they're dealing with and processing. So they compete on benchmarking. And so that's what happens today, right? And this is everything that I've talked about, everything that was formulated in the beginning by the foundational publications on chemoinformatics continues to be today. And then model validation. Here's the direct title of one of Pat's recent blog, Comparing Classification Models. You're probably doing it wrong. And he goes into great extent explaining how you cannot just compare models by statistics assigned to fixed values, because values have distribution and we need to take distribution into account. So really simply written, but very powerful blog. So I want to use a few recent examples. We're talking about chemoinformatics done in 2023, 2024. And what's new compared to what I called foundational chemoinformatics. And here is our own recent exercise, which should have been, as I thought, an exercise that will take a few hours of one of my graduate students' time, because we've been made part of a very large project at UNC and direct antiviral drug discovery. And we decided to look across Campbell database to see if people have discovered broad spectrum antivirals previously. So the task was to go into Campbell, identify all antiviral assays, identify compounds tested on those assays, and then look up if the same compound showed activities in different assays, right? A few minute exercise. However, what Holly Martin, the graduate student working on this, discovered is that the way the data is written in a highly curated Campbell data set, and we've complained in the past about curation efforts, and they fixed it. Many things have been fixed. I've published about it. But what you want to know, if you're comparing molecules tested in antiviral assays, you want to know the type of the assay, and you want to know assay conditions so that you could compare apples and apples, naturally. When it comes to assay conditions as recorded in the database, what do we typically want to know? It's antiviral assays. We want to know the virus, cell, assay, time, penetration assessment. One of the common ways of recording the data in Campbell, a molecule had antiviral activity against SARS-CoV-2. End of story. Best case scenario, very elaborate description. Small number of data, but that's the ideal case scenario. And there is a huge spectrum in between when the cells are mentioned, the virus is mentioned, but no experimental conditions. And you're left to wonder whether it was left out from the primary publication or was never recorded. And so Holly then started, and I asked you to document the amount of time. I'm talking about the most simplistic task, preparing a data set, which typically people describe on the publication one line. I prepared a data set. Okay. So Oakley phenotypic assays were missing the cell type. The most critical parameter of phenotypic assay, in what cells was the assay conducted. It was found in the assay description, but not where you expect to find. So she needed to extract this from the assay description, or it was completely missing. 64% of the data, it was recorded, but not in the right place. And in some cases, it was not recorded. Time spent 150 hours. Sure, graduate salary is relatively low, but still not something. And again, it's against expectation because we're talking about processing easy to get data that should be really. So that was that. So total time, 200 hours just dealing with phenotypic assays. And then Paul recognized that if you search with the most common, most obvious qualifier, bioassay ontology, definition of assay type, you would have missed 99.4% of all the data because the data was there, but not in the right place, not in the right column. And so retrieving data is critical, and as much as mundane as this task appears, as simple as this task appears, but if you don't have the data, you don't have the models. Or if the data is mislabeled, you don't have the models. And so for new and old people in the field, and I always emphasize this, we have to spend time, and typically frequently manual time, cleaning the data, preparing the data. It's unexciting. You cannot get an NIH grant for it because you may succeed on significance, perhaps impact. You will never succeed on methodology because there is no methodology. There's no innovation in methodology. There's no innovation. So if you take standard grant scoring criteria, you're not really going to get the grant. So what was supposed to be a few hours of work turned out to be a good portion of a graduate student thesis. And in the end, she's built a database called SMAC, and we're using this database to ask questions and building the second version of this database now for host-directed therapies, sort of the same idea of looking up or enabling people to look up the data and compare compounds that they find against compounds found in the database. other aspects of the field. So that was a little bit depressing, but not unexpected. What else has been happening in cheminformatics recently? And this is a publication from Connor Colley, who is in the room and who is speaking later here. And I chose this publication because it, I think, reflects the sort of transformation and transition in the field from relatively naive discussion, identification, and discussion of critical concepts to much deeper, much more rigorous, much more thorough analysis of the core concepts in cheminformatics, such as chemistry space. And this publication defined the concept of roughness of the chemical landscape as a way of addressing the same problem that I've alluded to, whether or not the data set is modelable, but again, at much more thorough level. But the aspects of this observation that I highlight talk about concepts that have been predefined. We're redefining the concepts that have been defined previously, but in more computational and theoretically rigorous way. And so that has been part of the modern cheminformatics, the influx of people who think much deeper and from a different perspective about problems that we have encountered. There are multiple publications that address issues of fundamental value to cheminformatics, but that's sort of the angle that I chose to introduce this paper. And then come most popular aspects of cheminformatics in the last few years, and that's what I've called going deep. Deep here, deep there, deep everywhere. And I want this part of the lecture to be very educational and not taken in the wrong way, because I'm going to be critical of ourselves as scientists and as cheminformaticians. And my first criticism is, when you develop a new methodology, or when you capture a new methodology, the most obvious reaction, human reaction, is excitement. And when you're excited, you don't see the light. You stop being objective. And then you kind of, I called it narcissistic modeling. Because you look at the reflection in the mirror and it excites you, because you're doing cool things. And so 2017, 2018, someone who shares the last name with me, along with other people, said we've never done this before, we're doing this for the first time, and we observe higher accuracy than those models developed with simple machine learning techniques. Of course, it's new, it's novel, you learn new things, you get excited. And you ignore some sober voices happen to be published at the same time, that it's not always provide deep improvement. But nevertheless, the excitement is there, and the excitement will always be there because we constantly invent new stuff. So you start analyzing deep learning papers deeper. Thank you. And here's one of the original publications from one of the original developers of deep learning methods, a hardcore statistician. With verbal statement, we found that deep learning methods significantly outperform all competing methods. That's a very powerful statement, especially the word significant, because this word is used colloquially or scientifically, and this is not a colloquial use of the word. And then you look at the actual data, because that's what we need to learn, how to look at the actual data, not the reflection in the mirror. And when you look at the data, what you find is that if you compare a deep neural net model with plain SVM or random forest, the largest AUC difference is 0.04 AUC units, the largest. And yet the error is an order of magnitude high. And it's just that. So we have to stop ourselves from using words that don't have very strict meaning, regardless of how excited we are. And here's another story. One of my favorite. Super bug killed by super drug. And it's a Cell. Cell is a very highly cited journal, a deep learning approach to antibiotic discovery. And a lot of hype associated with it in mass media publications. And that's another thing. I'll come back to this point in a few minutes. So what's behind it? What's behind it is a wonderful, highly appealing publication in Journal of Chemoinformatics and Modeling with a new way of learning how to represent molecules and how to compare molecules and how to build QSAR models of the highest accuracy. And today, this publication collected more than 750 citations. Very highly cited paper. There is a little red sign, if you go to the website, that most people probably miss, but I'm a sarcastic modeler. I clicked. If you click, it brings you to, and this is the original publication. As you could see, there is a very substantial improvement. So deep learning 0.8, random forest 0.6. Dramatic improvement, 20% better, 13% better, 26% better, 39% better. Deep learning models work much, much better. Only 8, actually it's 20. I was too lazy to replace all this line. So there are 20 citations of the red line publication. And it says correction. And what this correction says, that due to an error in processing of the random forest models, good old simple random forest models, you develop a new deep learning approach, but you cannot process random forest models. Right? The random forest AUC numbers were incorrect. And when you correct, you totally lose significant improvement. But who cares? Because you got a new bug and you got a new drug against the new bug. So who cares what happens with the method? Well, it turned out that this result was also recalled because it turned out that another lab 3 years earlier discovered that same compound and decided not to procure it anymore because it was toxic. Here's another story. What if you have the most unlimited computational power in the world? What do? You run, you discover drugs. And then you tell the world that you have the fastest supercomputer and therefore you're best in the world drug discovery because you run hundreds and hundreds of hours of supercomputer time. And the supercomputer, not a human, the supercomputer identified 77 new antiviral drugs at Oak Ridge National Laboratory. And it was published, not in Nature for some reason, a little bit suspicious, but nevertheless enough to get publicity. And then the same group had the guts of publishing a letter in New England Journal of Medicine, the journal with the highest, one of the highest citation value, how to discover antiviral drugs quickly, no less. And that's the consequence of pandemic. Thousands and thousands of drug discovery papers that appeared during computational papers. The world, everybody sits at home, you can't go to the lab, you can't make molecules. So you run docking studies and you publish papers. And that's the pandemic of drug discovery. The best comment I've read about publications discovering novel inhibitors or novel drugs, etc., was from John Cadera, who asked the question in his blog: is it really discovery of new inhibitors if there is zero experimental data? Maybe proposal, but even that's a stretch. Digital dreams of new inhibitors. That's how we should regard it. And that's a warning also. That's a warning of not being excited and using correct terminology. When we make discoveries, we make digital discovery. There's now a journal that's called digital discovery. So the next journal should be called Digital Dreams. And we all should be published there because without experiment, that's what we produce. We produce digital dreams. I found a wonderful quote from Richard Feynman, which I really want all of us to inscript on our head. We've learned from experience that truth will come out. Other experimenters will repeat your experiment and find out whether you are wrong or right. And although you may gain some temporary fame and excitement, you will not gain a good reputation as a scientist. And reputation is everything for a scientist. So we've published with Tudor Prier and Arthur Castle, who is in the room, a little feature that was called Surely a Joke in Mr. Document. And I encourage you to read it because we show there with data that all these predictions by supercomputer were experimentally shown to be inactive at the time when they were educating the world how to discover drugs quickly. So just to finish the sarcastic part, one of our colleagues had presented at AAA's meeting in 2019, kind of saying that we have to be careful, especially when we deal with big data and super powerful algorithms, that the algorithms have been specifically developed to optimize stuff. And the more data you have and the more computers you run, the better you optimize. And with more powerful computers that few people have access to, the computational experiments become irreproducible because nobody else has enough power to challenge and revalidate models. And so results, and I illustrated with a few examples, can be misleading and often completely wrong. There is general recognition of reproducibility crisis in science. I disagree with the last point. I don't think there's a crisis in science, but this is something that we have to be very, very careful with. And just to imprint this, there's a psychological rule of 3 repeats, right? If you want your kids to remember to clean dishes or clean the table, you have to say it 3 times. This is how we need to educate each other. So I've looked up the excitement with AI. What is if you say AI 3 times? And Urban Dictionary says it's a phrase used by most evil people with bad intentions. So please keep this in mind as you investigate new algorithms. That brings me to the impactful trends, and I'll try to wrap up. So why do we want new methods? This is the biggest transformation. I don't think it's methods. Many methods that we practice today have been contemplated, developed, or originated many, many years ago. The absolute biggest transformation of the discipline of chemoinformatics is because of the data. Because of immense, huge amount of data in every sense of the word. Here is a summary of current number of molecules in PubChem. Hundreds of millions of molecules with assigned biological activity. 41 million abstracts and 8.7. So European PMC for some reason is bigger than the American PMC. But enormous amount of literature. And as you know, enormous amount of literature really enable the developments of tools such as ChatGPT and alike. And constantly growing chemical libraries for virtual spring. And this immense amount of data challenges model development, challenges hardware, challenges human minds, challenges people who develop algorithms. And as we do it, again, I ask you to remember of problems and challenges associated with big data. So here is my summary of some of the trends in the field, and absolutely impossible to reflect on everything, despite the request that I had from Sasha. But this is what I consider emergent and factual studies. And what's really helpful, I mentioned in the beginning that there is no way I could cover in one lecture what is important. And I actually love this quote: the public have an insatiable curiosity to know everything except what's worth knowing. So these are sort of my list of things that are worth knowing. Ability to model increasingly large and complex, for instance, chemical mixture data, and screen ultra-large chemical libraries. That's emerging. Continue to emerge as a challenge in front of us. New algorithms enhanced by machine learning to improve both efficiency and accuracy of models. Instant integration with experiments. I think Gisbert published a paper defining DMT, or was one of the first people defining design, make, test, analyze cycle. The cycle used to be disconnected. We design, we make, and then someone tests, and then someone synthesizes. Self-driving labs and intelligent chemical design, what's emerging are algorithms that work at the level of building blocks, which is still smaller than the size of modern libraries. There are 50, 60 billion compounds, and there are interesting algorithms continue to emerge that look at the space and mine the space of building blocks. In silico in build, I will not going to talk about I will talk about a few points just to illustrate. It's becoming increasingly important to work with scientists conducting in vitro experiments and combining silicon in vitro to develop models that provide reliable alternatives to animal testing, both for toxicity testing and for testing for biological activity. And then cross-disciplinary knowledge integration and mining to achieve clinical impact. And I would like to suggest that focusing on ways of achieving clinical impact through chemoinformatics research is one of the outstanding hot challenges in chemoinformatics these days. And then endless applications beyond QSAR, what I define at some point as QSAR without borders. So that's the summary. Let me give you a few examples, some research in our lab, some not. What I also said here, this is what's really helpful to define trends. Just look at the lecture titles in this workshop because the program is outstanding and it captures all the current and emergent topics that I cannot cover, and nobody could cover in one lecture, but the entire workshop really stand out when I looked at the program in terms of topics that will be covered beginning tomorrow. One of the challenges that our group found exciting is how to achieve ultra-fast virtual screening. There have been publications, I mentioned 50 billion compounds that NMN released recently in their library. So it's very hard, and it's important and impossible to use traditional methods. Matthias is here, and his company has been developing or published one of the first, not published, sorry, released one of the first algorithms to enable rapid searches. But the challenge was out there, and people have been developing solutions, right? And why is it difficult? Ultra-large libraries and traditionally high feature dimensionality. If you think about making 50 billion comparisons using 1024 sized fingerprints, that takes time. That's what makes things really difficult. And so what I want to share is an approach that we have developed over the past year and that was the challenge in front, to enable querying of billion-sized libraries rapidly, using as little computing power as possible, and allow concurrent queries and free to use. So what's behind it is what has constituted the sort of the depth of deep chemistry in the last years, and that is the transition. And we've 5 people who speak at this workshop co-authored a paper last year, Gisbert and Sasha and Olis and Art, so they're all in the room. And we co-authored a paper on what we call the emergence of deep QSAR, and that what we highlighted there is the principal difference between old QSAR and new QSAR, and that is that we operate not in a traditional computed chemical descriptors, but in the embedded space. And so the embedding enables different ways of transforming chemical reality and dealing with chemical reality. And one of them, as has been shown in Professor Varning's group, and Ileana is going to give a lecture about chemography, is that this type of representation allows us to ask questions, and traditional questions, in a different way, and calculate chemical similarity and address the issues of chemical landscape in the way traditional descriptors disallow. And so one aspect that we have investigated and noticed is that as we run different types of encoders and autoencoders and transformations in the latent space, chemical similarity is not by default preserved. And when you analyze the distances between compounds in the latent space, as illustrated here using naive types of autoencoders, compounds tend to disaggregate even if they're similar in the original chemistry space. And so we've developed an algorithm that we call structurally aware latent space or autoencoder that address the specific issue of how to encode molecules in the latent space while intentionally preserving similarity between them. And one of the fundamental questions that we've asked that I encourage every group to discuss, and the discussion becomes hotter and hotter, and more informal, the more beer and other beverages like that you consume. And that's the discussion about what is chemical similarity. So what we have decided to use is what I think may be discussed as a fundamental chemical similarity metric, and that's graph-edit distance, because that is a mathematical concept. It's hard to calculate, especially if you want to compare it to very different molecules. But you could define similarity and objectively and not using any particular descriptors directly from the chemical structure and chemical structure representation as a graph. And in order to train the model, we've developed large data sets of analogs, and each molecule in this data set, the anchor molecule is taken from Campbell, and then immediate analogs with one graph-edit distance continuously is developed. 5 to 10 analogs are developed, and they are guaranteed to be nearest neighbors of each other in the objectively defined chemical graph space. And then we run the encoder. And what this slide illustrates is that as we embed molecules, we preserve original graph-edit distances calculated in the chemical graph space. And in more broad sense, here is a comparison of the distribution of Euclidean distances. On the left, naive autoencoder. On the right, salsa space, which preserves chemical similarity intentionally because that's built into the algorithm. And what's the use of it? The use is that we control the size of the chemical space, and we could decide which size of the latent space we want to use to encode molecules while preserving chemical similarity. And what we have shown is that SMALSA, which is a version of the salsa with small size latent space, preserves chemical similarity much better than when you use fingerprints, and at the same time enables the fastest computational speed as we compare distances in the embedded space with chemical graph distances for compounds even arbitrarily chosen. My second example of addressing a fundamental concept of chemoinformatics in sort of novel way is revisiting the concept of data balance or imbalance. And as I mentioned initially, we advocated for the use of balance data. The objective here was to train a model with available data to distinguish standard objective active from inactive. But there is a caveat that everybody observes typically when you look at large data sets from sources such as even Campbell, let alone PubChem, is that the most training sets are imbalanced. And when we nominate compounds from huge virtual libraries, we know a priori that very small fraction of those compounds, even if all of them are tested, will turn out to have the activity, the desired activity. So the training sets are imbalanced in practicality, and the external virtual screening sets are hugely imbalanced. And what we've realized, and that's the paper is in archives, that we need to change our historical trends as to how we've been building models and change the metrics that we use in order to enable the recovery of the largest number of positive hits, because when we do virtual screening and then experimental testing, we are hunting for positives. We're not hunting for models with the highest balanced accuracy. And so, and then the practical aspect of this work was that typically people screen compounds in batches in well plates. And so what we used here is positive predictive value as the metric of accuracy, estimated on selecting 128 compounds from the external set. And sets were created from PubChem, split into train and to nominate from test set, and they were intentionally imbalanced, both the training set and external set. And what we found that, and this is a comparison between balanced and imbalanced in 5 different data sets, is that when we train models to have the highest positive predictive value, we achieve the highest, much higher positive predictive value in the external set than with models trained traditionally with balanced accuracy. And that's the last column here, more vividly illustrated in the next slide when we compare the performance of traditional models and models emphasizing non-traditional, non-standard metric of validation such as PPV. A few comments about trends that I find emergent and important, and they will be covered in this workshop, such as AI/ML enhanced generative chemistry. So Gisbert is going to talk about it tomorrow. Design, make text, analyze cycle, integration within SDL. So this is what I illustrate here is a publication from Elaine Asper-Guzik work several years ago, but there is an absolutely strongly emergent trend in integrating computations inside the MTA cycle implemented within self-driving lab. And so I think it's an important area of research. And of course, various machine learning accelerated calculations that are made fast and accurate. And so Ole Sisayev is going to talk about this paradigm of ML enhanced calculations as applied to quantum mechanical tasks, I think on Friday. And Deep Dokken, that Art, who made it despite the bad train performance, as promised, developed Deep Dokken. So I'm going to hear about that from Art. I'm going to skip our own work and sort of extension in the interest of time and talk about the last topic, the importance of integration of chemoinformatics with clinical work. And even though traditionally we're focusing on ligand discovery and target discovery as standard chemoinformatics tasks, what is emergent is holistic understanding of the entire pipeline from left to right and development and application of chemoinformatics or chemoinformatics-like techniques to address the entirety of the pipeline all the way to the last point, which is adherence, precision medicine, and drug application. One particular area that is re-emergent to be exciting is called drug repurposing, which is application of drugs, existing drugs for new applications. And to me, this is one of the most exciting potential type of research for chemoinformaticians because it could make an immediate impact in the clinic if you suggest an existing drug to be repurposed for a novel disease. Physicians have the right to using these drugs in clinic if they are convinced that they could do it, and there is nothing against it. And here is a story that I found fascinating, inspirational, and motivational about a new colleague of mine named David Feigenbaum, who is showing here more than 10 years ago on the left, an athlete from UPenn who got stricken by a rare disease called Castleman and had his last words essentially and was nearly dying. So two cases of clinical death. This is how it looks today. And what he did was that he reasoned over data on himself, on his own. And once he was diagnosed with what's called idiopathic multicentric Castleman disease, what he learned about himself is that he had elevated cytokines, increased expression of one of the proteins and T-cell activation. So I asked the question, is there any drug that could regulate those clinical phenotypes? And he found sirolimus, an mTOR inhibitor, known to be used in patients that received organ transplant and performed poorly, and the organ is rejected, and there is toxicity associated with it. So he likened symptoms that he learned about in his medical research or medical training of patients with organ transplant rejection and his own symptoms, and decided, and his doctor basically said, you're dying anyway, why not? So he's been in remission for 10 years and published a New York Times bestseller about how to cure your own, chasing your own cure is the title of the book. So, this is a slide I think we all know about drug repurposing and how potentially expeditious could the drug discovery be if we do this. And we also have been exposed to a recent case of drug repurposing by Benevolent AI, who nominated baricitinib as a potential drug of choice for COVID as early as in February of 2020, just a couple of months after the world learned about this disease. And the way they reasoned was that we have a viral entry and it leads to inflammation. So it's a very simple reason. And so what is behind inflammation? Cytokine signaling, which is mediated by a few kinases. What works on those kinases? A few drugs, but baricitinib specifically, is a polypharmacology drug that inhibits all three kinases involved either in endocytosis or in cytokine storage. And so that was sort of the reasoning that they used to nominate this drug, looking at what historically appears as and remember, chemical systems biology is one of the areas of chemoinformatics in the original publication. And what they really used was what's called a knowledge graph. And knowledge graph studies, I find probably one of the most exciting projects around lab and in labs that are studying knowledge graphs, which have been introduced by Google and allow people to answer really bizarre questions, such as what is common between Da Vinci and the Eiffel Tower? And you must be deeply drunk or nuts to ask a question like this, unless you have access to knowledge graph behind Wikipedia, which says that Da Vinci painted Mona Lisa, which is in Louvre, which is in Paris. Now, that's a path through the knowledge graph, and it's a crazy path. But if you contemplate the process of consolidating the world knowledge distributed across multiple data, clinical, non-clinical, chemical, biological, biomedical, historical, medical, clinical, etc., and integrate this knowledge, compiled by domain scientists and stored in databases, integrated with inferences made from this data to affect what domain scientists do in their labs. That can be done through knowledge graph construction, knowledge graph curation, familiar term, knowledge graph compression, knowledge graph completion. From computer science perspective, knowledge graph completion is the same as making predictions about new edges that connect two semantic objects, such as a drug and disease. And that effectively means an elimination of a new drug for a new disease, predicting this particular new connection. And so there are multiple algorithms being developed. Again, I find this very exciting for a chemoinformatician to work on this. The simplest approaches that can be used is to discover rules that connect known or that are behind biological pathways that are behind known drug disease connections. And then these rules can be used to forecast whether a drug and disease that have a connected path found frequently in association with drugs and diseases could be repurposed for a new disease. And I'm part of a huge project recently awarded to David Feigenbaum by ARPA-H to examine, and this is a familiar territory, all against all similarity searches, all against all docking calculations, all against all biological, biomedical graph mining to calculate the strength of association between every drug and every disease. And through this integration, searches, and identification of scores, the hope is that relatively low-hanging fruits will emerge, similar to the story of David Feigenbaum curing himself, that can be tried in the clinic. And so that's a chemoinformatic type analysis of a knowledge graph. Remember, chemicals are graphs. And here, again, we're back to the concept of graphs and ways of mining graphs that are familiar to us as chemoinformaticians in order to repurpose drugs and nominate them for clinical trial. I promised that E equals MC squared is a universal formula. And I found this picture, the real mean of EMC, E equals MC squared. So that's not mine, but what is mine is the new formula of scientific discovery that I share with you and encourage you to use. And that's what my talk was about, how to combine modeling and curated content. And so that together really creates opportunities for new scientific discovery. Overall, my last two slides. As chemoinformaticians, we depend on data, tools, and challenges. And when these three objects, semantic objects, are combined, a new hypothesis could emerge. Now, hypotheses have to be validated and filtered out. So filtering as building filtering models is very important. And after filters, a value is created. Sasha talked about investors. So that's the point of interaction with them. But value is not necessarily dollars, it's a new knowledge that goes back and fuels data, tools, and challenges integration. It takes a village, it takes learning, it takes multiple scientists interacting with each other. Someone once asked me if I have drawn this particular picture of scientists working with each other. I said, no, it was Picasso, but I was puzzled by the question. In my personal opinion, and I'm allowed to share my personal opinion. My personal opinion, there is another missing element of this entire workflow. Thank you for giving me a cup of coffee before this lecture session. It certainly was very helpful. And then I'll end with last two slides. I've talked a lot about hype. This, you may have seen this. This is Gartner, is a consulting company that publishes stuff like this, hype cycle. So hopefully with computer-assisted drug discovery, we're beyond this hype. And we're into what's called plateau of productivity with all the methods. So I'm ending on really positive note despite multiple criticism that we've heard. So this is the summary. Again, I'm not going to read it. I've talked about big data. I've talked about exciting developments, really the interface between computational organic chemistry, tools and data sharing. There are many, many topics I have not talked about. And with that, my last educational comment from Derek Lau. It's not the machines are going to replace chemists, it's the chemists who use machines. I really love this quote, will replace those who don't. So that's what everybody is learning here today. Thank you very much.
So we have time for one short question.
Wonderful. Alex, I think you made it up that it's extremely important that the experiment will always validate. How do you deal with the knowledge that 80% of what is published in biology is
crap? You can't. But there is ongoing effort. I didn't have time to recruit to discuss. There are two ongoing efforts. I highly support the concept of self-driving labs because it's data generation, clean, in situ, reproducibly, right? So essentially what I'm saying is we cannot fix the past, but we could change the present and the future. And second ongoing effort that Structural Genomics Consortium is pushing is a new effort in generating high quality data using various types of experimental tools, sharing this data. There's a database called AirCheck that they're creating, and basically having the community effort to build it. But I don't think there's anything we could do with past data.
Okay, just I would suggest to move the discussion to the welcome part. Otherwise, actually, we need to choose either have some drinks or stay with. So, thank you, Alex.
Thank you.